Hi, my name is Ines Chami. I'm a PhD student at Stanford University, and in this video, I will present our work on hyperbolic knowledge graph embeddings. This is a joint collaboration between Google and Chris Ray's group at Stanford. This talk will be split into three sections. I will first start by going over some preliminaries and introduce the problem of knowledge graph embedding. I will then present our model for hyperbolic knowledge graph embedding, and finally, I will go over some experimental results. So let's first review the problem of knowledge graph embedding. Knowledge graphs are relational data structures used to store facts about the world. These knowledge graphs are widely used in industry that deal with large volumes of data, as they can serve as structured repositories for information. In these graphs, nodes represent entities such as famous people or places, and edges represent relationships between them. Facts in knowledge graph are often stored in the form of triplets head relation tail. An example of such triplet in this knowledge graph is the Eiffel Tower is located in Paris, where the head entity is the Eiffel Tower, the relation is located in, and the tail entity is Paris. One major challenge is that knowledge graphs are often incomplete, as we cannot enumerate all possible triplets. In this example, for instance, Barack Obama is Sasha and Malia's father, and that implies that these are siblings, even if that triplet is not in the dataset. One approach to overcome this challenge is via knowledge graph embeddings. Formally, embedding method map these discrete entities to continuous representations such that the input graph structure is preserved in the embedding space. The geometry of embeddings can then be used to infer new facts and complete the knowledge graph. For instance, since Sasha and Malia are both close to Barack Obama in the embedding space, we can infer that these two should be related. However, we face a challenge here since knowledge graphs exhibit complex relational patterns. For instance, some relations might have a hierarchical structure, such as the relation father in this toy example. These hierarchical relations are unidirectional, and if a triplet head relation tail is in the knowledge graph, this does not imply that the reverse triplet is in the knowledge graph. On the other hand, some relations might have very different patterns. For instance, the relation married here is symmetric, and Barack Obama married to Michelle Obama implies the reverse, Michelle Obama married to Barack Obama. Preserving all these patterns in the embedding space is challenging and requires flexible embedding methods. Formally, knowledge graph embeddings are usually learned by solving a link prediction task. In this task, the input is a head relation query, for instance, who is married to Barack Obama, and the goal is to return the most likely tail entity. To do so, knowledge graph embedding methods rely on three key components: embeddings, which are used to represent entities and relations; a query embedding function, which applies a relation-specific transformation to a head entity embedding and produces a query representation; and a scoring function, which measures the likelihood of a given triplet and is used to return the most likely tail entity. A typical way to define such models is via Euclidean embeddings. The model parameters are the embeddings themselves, and these are optimized such that scores of true triplets are high. A popular example is the Trans-Z model, where the query function is a simple translation and the scoring function is the Euclidean distance. These Euclidean embeddings achieve good performance on missing fact recovery. However, to capture all the complex relational patterns found in knowledge graphs, these methods usually learn embeddings in very high dimensional spaces, which is expensive to store. Having introduced the problem setup, I will now describe our approach for low-dimensional knowledge graph embeddings. Concretely, our goal is to have high flexibility embeddings with fewer dimensions than what typical Euclidean methods use, and our approach relies on two components: hyperbolic embeddings, which can effectively capture hierarchical patterns in low dimensions, and attention-based relational operators, which can effectively capture complex logical patterns in knowledge graphs. Here we turn to hyperbolic geometry, which is a non-Euclidean geometry with a constant negative curvature. Curvature measures how an object deviates from a flat Euclidean object, and curvature 0 recovers the Euclidean geometry. It has been shown that hyperbolic embeddings can effectively represent hierarchical data in low dimensions, and in particular, there are some theoretical results showing that any tree can be embedded almost perfectly into hyperbolic space, but this is not possible in Euclidean space. At a high level, this is because hyperbolic geometry is some sort of continuous version of trees. To give more intuition, the volume of balls in hyperbolic space grows exponentially with radius, similar to trees where the number of nodes grows exponentially with depth. In this circle limit illustration, for instance, all triangles have the same size in hyperbolic space, but we see that as we get closer to the circle boundary, things appear to be infinitely smaller, illustrating the exponential growth property. Since knowledge graphs exhibit a lot of hierarchical relations such as father or mother, we propose to learn embeddings in a curved hyperbolic space which has more room to fit the complex hierarchies. To do so, we define the embeddings themselves to be in hyperbolic space, and rather than using the Euclidean distance function to score triplets, we use the hyperbolic distance function. Note that some relations might not be hierarchical, and we therefore propose to use different learnable curvature parameters depending on the relation involved. We will show that this is key to achieve good performance on the link prediction task. We're still missing one key component here to have a complete pipeline, which is the query function that applies a relation-specific transformation to entities embeddings to return a query embedding. In other words, how do we map a head relation query to a query embedding in hyperbolic space that captures both the entity and the relational information? Note that simple Euclidean transformations such as translations are not valid operations in hyperbolic space. In this work, we explore two types of geometric transformations to model logical patterns in knowledge graphs, namely rotations and reflections. In Euclidean space, people have explored rotation operators to model logical patterns such as anti-symmetry or inversion, and they found that indeed this transformation yield improved representation compared to simple translations. Additionally, we propose to use reflections to represent symmetric relations, since applying a reflection twice yields the identity operator. This leads us to the questions of how can we parameterize these rotations and reflections in hyperbolic space, since Euclidean operations usually don't apply there. Luckily, on a specific model of hyperbolic space, the Poincaré ball, and when these operations are centered around the origin, then hyperbolic rotations and reflections coincide with their Euclidean counterparts and are isometries of the hyperbolic space. That is, the geometry of the space is preserved after applying these operations. In practice, we can parameterize these operations efficiently with given transformations, and I invite you to take a look at the paper if you're interested into technical details here. In the previous slide, we've introduced two types of geometric operators to capture logical patterns in knowledge graphs. However, one operator might work better on some relations while the other works best on others. For instance, symmetric relations might be better represented with reflections, while rotations will better represent antisymmetric relations. Here we propose a hyperbolic attention mechanism which uses neural attention to determine how to combine the two hyperbolic operations for a given relation. The key here is to leverage the tangent space, which is a local approximation of the hyperbolic space that has a vector space structure, and where we can perform operations such as dot products or averages. Note that this attention mechanism can be applied beyond rotations and reflections to potentially capture even more complex logical patterns in knowledge graphs, and we leave this as future work. Let's now recap our proposed approach for hyperbolic knowledge graph embeddings. Given an input head relation query, we first extract entity and relations embeddings. Note that entities embeddings are defined in a curved hyperbolic space where curvature is relation dependent and can be learned. We then apply relation-specific hyperbolic rotations and reflections to the head entity embedding and combine these with hyperbolic attention. Finally, we produce an answer by taking the argmin over the hyperbolic distance function. In practice, the embeddings and curvatures are learned and can be optimized by minimizing a loss function defined on true triplets. We now move to our experimental results to understand the benefits of using hyperbolic embeddings and attention-based transformations. First, we compare our approach to standard baseline on three popular knowledge graph datasets for the link prediction task, where the goal is essentially to predict the correct tail entity for a given head relation query. We evaluate performance in a low-dimensional regime using only 32 dimensions, which is an order of magnitude smaller than what typical Euclidean methods use. As expected, we observe improvements in performance compared to state-of-the-art Euclidean embeddings on all benchmarks. Further, we also compare to MURPI, which is a translation-based hyperbolic method, and find that our approach obtains better results. This suggests that modeling logical patterns with rotations and reflections and attention yields better knowledge graph representations. Next, we analyze the role of curvature on the WordNet dataset, which contains a lot of hierarchical relations such as hypernymy. We compare our approach, which uses a trainable curvature parameter for each relation, to a hyperbolic baseline with a fixed curvature parameter, and to an Euclidean baseline, which is equivalent to setting the curvature to 0. We observe that in low dimensions, both hyperbolic models improve over the Euclidean baseline, confirming that hyperbolic geometry yields better embeddings in low dimensions. In high dimensions, we observe that Euclidean embeddings have the best performance and trainable curvature recovers the Euclidean geometry. On the other hand, fixed curvature degrades performance, and this is due to trade-offs with machine precision, curvature, and dimension. In summary, using a trainable curvature parameter results in better performance in both low and high dimensional regimes. Finally, we also analyzed the benefits of using attention-based transformations on relations from the Diago dataset. We compare rotations and reflections only to the attention-based model. We use data statistics to categorize relations into symmetric and anti-symmetric categories and find that attention-based transformations always improve over rotations and reflections only. This confirms that the attention-based model has the flexibility to pick the right operator for a given relation. To summarize this talk, we've introduced a hyperbolic knowledge graph embedding model to learn low-dimensional knowledge graph embeddings. Our approach models entities as points in hyperbolic space and uses trainable curvatures. We model relations as geometric operators in hyperbolic space and use a hyperbolic attention mechanism to combine these and have flexible representations. Our method outperforms existing Euclidean and hyperbolic methods in low dimensions. We demonstrated that having trainable curvatures provide more flexibility to learn embeddings in both low and high dimensional regimes. Finally, we demonstrated that attention-based transformation can effectively capture logical patterns found in knowledge graphs. I would like to end this presentation by saying that our paper is online and we have open source PyTorch and TensorFlow implementations for this work. And feel free to reach out to me if you have any questions. Thank you.